Hi, everybody. In this lecture, I'd like to talk to you about electric power. So power is something that we covered in Physics 1. And in kinematics, we talked about the definition of power as being the energy transformed per unit time. Now, it's still that, okay? But in electrical power, remember that what's happening is you have a change in, say, for example, electric potential energy as a charge moves through a voltage. And the relationship in between the change in the potential energy as the charge moves through the voltage is the change in potential energy U is equal to the charge times the change in voltage, or QV. So we can write the energy transformed now as QV, and then we'll write the time as divided by T. So power would be QV over T. Now, we've already defined the current in a previous lecture as the charge divided by the time. And so Q over T is I. So we can write the power, electric power, is equal to the current times the voltage. Now, just like in our last semester of physics, the unit of power is an energy per time, which is a joule per second. And the SI unit of 1 joule per second is 1 watt. So 1 watt is 1 joule per second. If the device is ohmic, then we can use Ohm's law, which is V is equal to IR, and we can write the equation P is equal to IV in other forms. For example, we could plug in for V and write V is equal to IR, and then we have I times IR, which is equal to I squared R. Or we could rearrange the current bit and say that the current is V over R. So we have V over R times V, which is V squared over R. So P is equal to IV is equal to I squared R is equal to V squared over R. Those are all valid power equations. Now, one thing that's important to understand is that when you pay your electric bill or your power bill, you're not really paying for power, but net energy, which is the power consumption that you've used times the time for the whole month. So one common unit, instead of saying joules, the joule is actually a really small unit of energy for a household power consumption. And they don't want to freak people out by having their energy usage in millions of joules. So instead, they talk about the kilowatt hour. Now, the kilowatt is 1,000 watts, which is a unit of power, and then you multiply by the time, and the time here would be an hour. So a kilowatt hour is 1,000 watts over 1 hour. Now, 1 hour is 60 minutes times 60 seconds per minute, or 3,600 seconds to put everything in SI units. So 1,000 watts times 3,600 seconds is 3.6 times 10 to the 6 joules. So lots of times, if you look at your power bill in terms of its consumption, you'll see your energy consumption in kilowatt hours instead of the SI unit of energy, which is joule. So I thought I'd do an example problem based around this idea because a lot of students find it confusing. So this is one I kind of made up. Many households have replaced incandescent light bulbs or old school light bulbs, which are just twisted tungsten wires. They've replaced those incandescent light bulbs with light emitting diodes, or LEDs. And that's because LEDs are more energy efficient. So for example, a 60-watt incandescent light bulb can be replaced by an LED bulb that only uses 9 watts, but these bulbs would each produce the same amount of light. Now, if electricity costs 12 cents per kilowatt hour, how much does it cost to run a 60-watt incandescent light bulb versus a 9-watt LED bulb for a year? So let's talk about that. All right, so first we need to find the number of seconds in a year. So 1 year is 365 days, and then multiply it times the number of hours in a day, which is 24, and then the number of minutes in an hour, which is 60, and the number of seconds in a minute, which is 60. And 365 times 24 times 3,600 is 3.15 times 10 to the 7 seconds. So that's about how many seconds there are in a year. Now, to get energy, you multiply the power times the time. So let's say that we burned each of these bulbs nonstop straight for a year. So you burn a 60-watt incandescent bulb for a year. First of all, good luck getting it to not burn out during that year, but there you go. So 60 watts times 3.15 times 10 to the 7 seconds gives you 1.9 times 10 to the 9th joules of energy consumed by that bulb. Whereas the 9-watt LED bulb would be 9 watts times 3.15 times 10 to the 7 seconds. And that has an energy consumption of 2.8 times 10 to the 8th joules. Okay, so now let's convert joules to money, which is probably something you never thought you'd hear anybody say. So 1.9 times 10 to the 9th joules, right? what you would do is convert the joules to kilowatt hours by dividing by the conversion, which we discussed on a previous slide, is 1 kilowatt hour is 3.6 times 10 to the 6 joules, right? And then you want to convert from joules to money. So 1 kilowatt hour costs you 12 cents. So you're multiplying by $0.12. So doing all that, plugging it into a calculator, you can see that it would cost you $63.07 to run that incandescent light bulb straight for a year. Whereas the 9-watt LED bulb, which consumes 2.8 times 10 to the 8th joules of energy, would cost you $9.45 for that same year. So thinking about it that way, yeah, LEDs might be a little bit more expensive than traditional incandescent light bulbs, but over the lifetime that you would use the bulb, they actually save you a decent amount of money. Now, in a household circuit, the wires used in homes, there's a lot of regulations surrounding this electricity, and for very good reason. The wires that are used in homes that carry electricity have very low resistance, but if the current's high enough, the power will increase. And as we discussed in a previous lecture, when you run current through a wire, it gets hot. And sometimes that can become hot enough to actually start a fire. So to avoid that, to avoid pulling too much current through the wire that will cause the wires to heat up and start fires, we use things called fuses or circuit breakers. And then those things actually disconnect when the current surges above some predetermined value or level. So this is what a circuit breaker might look like in a typical household. And you might have to go, for example, and if there's a surge or a lightning storm or something like that, you might have to go and flip your circuits back on when they flip off. Now, fuses, though, those are one-use items, and if they blow, the fuse is destroyed and has to be replaced. So you might have had to replace fuses in your car or other types of electrical devices, and they usually have this ribbon or something like that in the inside, this ribbon of metal, and then when they blow, you can see that the ribbon has been broken, and so you don't have a complete circuit anymore, and that's how they work. And then when that happens, you just replace the fuse. So circuit breakers are a lot more common in homes than they used to be. And those are switches that will open and close if the current is too high, and then you just reset them. Okay, and this is kind of a little schematic on how that works. So you have a circuit breaker that's closed, and then there's a little spring loaded in there. And then what you have is that when the current is flipped, the little bimetallic strip, which will then, open and shut because the heat will cause it to expand and contract differently, which will cause it to bend. And then that causes the spring loading here to move contacts to open, and then you have to go reset it. So that's something that you might see in circuits. All right, now most of the household power that you have is actually alternating current and not direct current. So what that means is that rather than having a constant voltage like from a battery, you have a voltage that oscillates sinusoidally. And you can see here what that might look like. So for a battery, you'd have a nice constant current, a constant voltage, so it's just a nice straight line, and that's DC or direct current. But for alternating current, you'd see this sinusoidal variation in both the current and the voltage. So that's actually what's coming out of the wall sockets in your home, is this oscillating voltage source, okay? And mathematically, that might look like this with a sinusoidal function dependence, okay? Now, because we still just need to give a value, you can see in these graphs, for example, that you've got a current or a voltage that's oscillating. And so if you tried to figure out what the average value of the current or the voltage was over time, it spent as much time being positive as it does negative. And so the average would actually be 0. So we don't talk about the average current or the average voltage, because in AC that's 0. So instead, what we do is we talk about the root mean square current or voltage. So to find that, what you do is you take your current or voltage and you square it, and then you take the square root of it, which gives you a positive number. And that yields your root mean square, or RMS value of the current or the voltage. And that gets you away from the average, which would just be 0. So if you square something and then take the square root of it, what you're doing is you're getting about 71%, or 0.707 times the peak magnitude of the current. So if you go into here and you look at what your maximum current value is at the top of this little sinusoidal value, your root mean square current would be about 71% of that value, if that makes sense. And the same idea for the voltage, okay? So in the United States and Canada, your RMS voltage, typical values for that is about 120 volts. So you have 120 volts RMS voltage coming from the wall socket in US and Canada for traditional or standard outlets. You can get higher values of voltage for special outlets in the home. For example, if you wanted to run a dryer and you wanted it to have a higher voltage, you could run a special wall socket for that. But for most of the wall sockets in your home, they're 120 volts. But in Europe, Australia, and Asia, 240 volts is actually a typical RMS voltage wall value. Okay, so you'd see a different value there. Not only that, but if you travel to another country and you look at their wall sockets, their plugs are also usually different shapes. I mean, if you think about it, it doesn't make sense that everywhere in every culture, all the wall sockets would look exactly the same anyway. And so what you'll see is if you travel to another country, you can actually buy adapters. And what you probably want to buy is an adapter that will adjust the voltage, have a transformer in there that will adjust the voltage so that you don't blow all your blow your hairdryer out or whatever. And also changes the shape of the plug. So here's, for example, what the plugs look like in different countries. Here's the US, here's the EU, here's Australia, and here's the UK. So you'd have adapters for your devices if you go different places. Okay. All right. So I hope that makes sense, and I hope you understood all that, and I'll see you in the next video.